Inside the engine, the oil encounters huge mechanical stresses and high temperatures, in excess of 1000 degrees Celsius. The oil has to act as a liquid bearing, carrying enormous loads. For instance, between the cam and valve follower, huge forces are trying to tear the oil apart. No oil could withstand that attack alone. A special zinc and phosphorus-based additive, ZDDP, is used to increase wear protection. The oil film also has to stay in place on the cylinder walls, pistons and rings to maintain compression, despite the forces trying to tear it away. As speed and load increase, the oil has to work even harder to stay in place and carry the extra heat away. At the same time, dispersant and detergent additives are needed to stop piston deposits building up. The oil splashing on the bottom of the piston and bore helps carry heat away from these pressure zones and down into the crankcase, keeping operating temperatures under control. All that burning produces carbon, soot, acids, varnish, and other deposits that oil additives must control. Temperature control is the single biggest challenge for motorcycle oil. Motorcycles use relatively simple cooling systems, compact liquid cooling, or a combination of air and oil cooling. The oil has to adapt to a very wide range of operating demands to maintain protection over time and in extremes of heat and cold. It must absorb deposits, yet must not oxidize or thicken. It has to be thin enough to flow easily through small oilways when cold, yet thick enough to keep on lubricating and coating components when hot or under load. But four-stroke motorcycle oil isn't just for engines.
It's more than just oil, it's liquid engineering.